Hey everyone, so this video is a bit an old video I made a little while ago, so let's say 1 month ago. I think it was a pretty interesting video speaking about the Monte Carlo integration, one very important and interesting method in fact, but I quite messed up the thumbnail and title, so it didn't reach a lot of people, and I wanted to try it again and see if I can make it better this time. So yeah, hope you enjoyed the video, leave a like, subscribe, and let's go. Hey everyone, in this video we will see how to compute complex integrals, for example this one, using the Monte Carlo method. We will then display our results in the form of a histogram to discuss and analyze them. I also provided a simple example that will help you understand the Monte Carlo in general, and we will compare it afterwards with a more classical method, which is the trapezoidal method. So sit back, enjoy the video, and let's go! Alright, so the Monte Carlo integration comes from the more general Monte Carlo method. It is a method widely used in basically any imaginable field. But in simple words, it is an algorithm that relies on repeated random sampling. It is a method that can help us break down complex problems with a very simple yet easy to use technique. The history behind it was back in 1945, so in World War II, where a mathematician came up with it when he was working on the neutron diffusion problem, a key concept in chain reaction and atomic weapons and so on. I actually made a video about this explaining the history of this method and how it got invented. If you're curious and want to know more, feel free to go check this video after watching this one. Now, before we discuss the integration method, we need to understand the fundamental idea behind the general method. So let's consider a very basic example called the human average example. Suppose you have a number of humans, you want to calculate the average height of them. Now, yes, you can compute the arithmetical average of them, like we know, the sum divided by the number of elements. But let's consider this simple example to use the Monte Carlo method. Now let's break it down in 4 steps. Step 1 would be to do a random sampling, where we will randomly choose a subgroup of humans we will study, say 3 humans. The next step involves modeling. So in our case, the computational model would be to compute the average height of the 3 selected humans. We repeat this process many times, where we will each time select 3 random humans and then compute the average. This is also known as simulation. And finally, we do a statistical analysis. In some cases, it is the form of a probability distribution, where we will display a histogram to see the results in terms of frequencies. Now let's try and solve this problem in Python. It will make things way more clear. Right, so here I prepared a Jupyter notebook file where I explain the human height example. So it is a very practical example, and suppose we want to compute the average height of 1 million humans. Now, actually, we want to compute 8 billion humans. It is humanly impossible to measure all the heights of humans, since some are somewhere lost in caves, some are in unreachable mountains, and so on. So let's stick with just 100 million. Instead of measuring each one, we randomly select a fraction of them, and then we apply the Monte Carlo idea by making a random sampling. So we select a subgroup of these people. We do our model by each time computing the arithmetical average. We repeat step 1 and step 2 until we are satisfied with the results. And we do our statistical analysis. Now here, we import the NumPy module, and we generate our height data of humans, for example. So I didn't have the time to measure 1 million humans, so I actually generated one random array using the normal rule, centered around 170 centimeters, with a 20 centimeter shift, let's say. And from these 100 million humans, we will randomly select 1 million samples. So this is what we will be working on. Now if I execute this, connecting to the kernel, all right, now this block is running. Now it might take time to generate 1 million, an array of 1 million size. So depending on the size, takes time. Now imagine if it was 8 billion. Now just to showcase it, if it was 8 billion humans, so the actual number of humans we have on this earth, it is unable to allocate 60 gigabyte of memory. So in a way, we will stick to only 100 million. Now, the next step is, let me hide this and make it like this. The next step would be to make a random sampling. So from this array right here, so the sub-height data, we select 100,000 humans. We again select a fraction of them by doing the np.random.choice. This will select 100,000 samples from this data right here. And then we compute the average height of this sample right here. This is also step 2 of modeling. Now step 3 would be to do it multiple times by simulating it each time. And since we want to compute the overall average of this value right here, we will append it to an array called list heights, which is this one. And we compute the overall average height we find in the results. Here I have 3 print statements. The arithmetical average calculates the average of the initial data of the 100 million data, which will we compare. The second is the average height Monte Carlo, so this one. And the third one displays the error. So you can already see here I've run this. Let's run it again. It might take a bit of time depending on these 2 values you chose right here. But you can see here that the arithmetical average is at 170.002, whereas the random sampling average is at 169.996 or 99.7, let's say, with an error of 0.0032, which is pretty close. I mean, we are just, let's say, a couple micrometers away. If we would run this line of code right here, which displays a histogram of list of heights with 50 bins, so the bins are these rectangles right here, a green color, alpha is just also related to the color, and an edge color of black, so we can clearly see each rectangle. Now what this means is that you can see here that some values right here are displayed, so this is the heights, and this are some integers. Now this represents the frequency of these results. For example, here we can see that we got approximately one time this result right here, whereas for 170 centimeters we got it the most, so it was the most frequent result. We have a 0.0032% error by comparing the 2 methods. Now remember here, we selected just 1 million samples out of the 100 million samples. So we took 1/100th of this initial data sample. Now imagine if you wanted to make the same with all the humans on Earth, instead of measuring the 8 billion humans, which would take weeks, months, or even years to measure, we can only measure, let's say, 10 million humans, or 1 million humans, for instance. We apply the Monte Carlo. That gives us a result pretty close of the actual value. So we can see here, compared to 100 million samples. Now imagine to get this result would take several years, whereas this one take, for example, just a couple days. So this is one application of the Monte Carlo which I find quite interesting. It is exactly by building this logic right here that you can actually compute integrals with the same procedure. Now what you can also do is increase the number of iterations in our simulation. And if you do that and rerun the code, you will see that our histogram is much more smoother and that it is more centered around the 170 centimeters peak right here. So these three values are the most frequent ones. You can also decrease the number of bins. We run the code. And you see now it resembles much more a normal distribution, with the most frequent value being the 170 centimeters, the closest one to the actual result, repeating itself almost 1,200 times amongst the 10,000 trials. All right, now that we are all set and prepared, we can develop the concept of the Monte Carlo integration. Like the famous rectangle and trapezoidal rule, it is a technique for numerical integration, but instead of going into discrete order coordinates, you take random ones. Here's how you can transform any integral into a Monte Carlo integral. In calculus, there is something we call the mean of a function, and it's defined as the average value of the function over its domain. Now, in a one-variable case, we define it as the integral of that function divided by its domain. When we speak about domain, we simply mean the domain of definition of the function. For example, in 1D, it will be a segment with length a, for example, between 0 and 1. In the 2D case, it is a surface, and in the 3D case, we often speak about a volume. Right, so the calculus concept is defined, but what about the numerical one? Well, intuitively, we can define the mean of a function as the arithmetical mean, and let's just pretend we do this. Now we got something interesting. But aha, remember, this is only an approximation. Though this might seem something revolutionary, but this is just a fancy way to compute numerical integrals in 1D. But let's focus on the sum right here of f of x from 1 all the way up to n. Now, instead of taking ordered uniform intervals like you would normally do with the rectangle rule, let's consider a set of coordinates randomly selected from the domain of our function. We will take these random points and evaluate the function at them. What we just did was the random sampling, so step 1. Now, remember, in our formula we have d, which represents the domain of definition. In this case, it's 2 minus minus 2, so 4. We compute the integral, which is step 2, modeling. We repeat the process as many times as needed, selecting each time a new set of random points and computing the integral. Finally, we compute the average of our integrals and analyze the obtained results. Now, there is a theorem called the law of large numbers that states if you repeat the process for lots of trials, the result obtained by randomness becomes closer to the actual expected value. Alright, now that we discussed all of that, it will be straightforward to implement it in Python. So let's go. Alright, so once again, here we are in our Visual Studio Code interface. By now, I think you already know how to make this Monte Carlo integral, but let's see. Now, we start as always by importing the NumPy module, so import NumPy as NP. Then we are going to define three variables, so the number of samples, which is equal to something, the number of random samples, and an array containing all the data. Let's call it E array, standing for integral array. So number of samples is the entire data group. So for example, let's say we have 100,000, all right? The n random samples is the random samples we're going to take from this bigger data set. Let's say we will just take 1000, and the array of integral will be set to an empty array, for instance. Now we will define the coordinate samples. So let me actually make this in a small s. So this will be equal to np.random.uniform. From 0 to 1, here you can define another variable called a is equal to, and then b is equal to. This will be the boundaries of our variable, but let's say they're all between 0 and 1. And for number of samples. So this will generate an array of elements between 0 and 1 with a size of 100,000 elements. Alright, we will do the same for y and z. So y, z, right? Now in contrast, these three represent, by analogy to our human height example, this represents the height data of our 100 million samples, if you remember. Alright, now we are going to perform our iterative for loop, so for e in range between 1 and then as much we want to run the simulation, let's say one or 10,000 times. Alright, we are going to choose 1 or n random samples from these three arrays. So let me do this. So x is equal to np dot random dot choice from x sample, like so, and n random samples. Let me do this for y and z. Now let me define the function and then we will explain what is actually happening. So I'll be copying it directly right here to not lose any time. So our function is equal to np dot exponential minus x squared plus y squared plus z squared times np dot sin of x times y times cosine of z. Alright, so what we are doing here is to select randomly 1,000 elements from these three arrays. We will then use these values to compute the function right here. This will result in an array having the same size of x, y, and z, so it will be 1,000. Alright. Now to compute the integral, remember it's the domain of definition d times the sum of the elements, so np dot sum of our function, divided by the number of random samples, so this one. Now since we are in a 3D case, remember v represents the volume of definition, since we have between 0 and 1 for all three cases. This will be the same as 1 minus 0 to the power of 3. Now all we gotta do is append this value right here to our array. So we are going to do a dot append the new integral which is computed. And believe it or not, that's everything you need to compute the integral. If you go ahead and print the result, we will see that the result is 0.06358, etc. Now let's actually draw a bar chart, or a histogram if you want. We will add the matplotlib module, so import matplotlib.pyplot as plt. And all the way down here, we will define our histogram by doing, well, let me actually just copy this and print it here. So what we are doing, we are defining a histogram with the plt.hist, and we will display the array of integrals we just computed with 50 bins. So let me actually change all of that. And we also need to define the figure and axis is equal to plt.subplots. Right, let's go. And let me change this. So we will run our code. Now we will get this result right here. Now let me actually zoom this. We see here we have these values. So these ones represents each time the computed integral. So one time we run the algorithm, it gave 0.06, another time it gave 0.068, etc. Now here you can see the frequency or appearance of each result. For example, for a result of, it was far less frequent to get a 0.058 result than it was to get a 0.062, for example. But the most important part are the ones here. you can see that the integrals here are far more likely to happen than the ones here, for example. So this means that our solution is somewhere here. If you would zoom a little bit further, you will see that somewhere between these 5 bins, so this one, all the way up to this one, here lies our solution. Now, to get an even better and precise solution, what we can do is increase the number of iterations we are doing right here. So let me add, for example, 1, 0. We rerun our code. Now this might take a bit more time because we increased by a factor of 10. By looking at our histogram, you can see that now it is much smoother around this area right here. You can see that it is more centered around this value right here. So these 2 values. If you would rerun the code another time, you will see even better results. But in a way, that is the most simple way to think of the Monte Carlo integration. First, so to summarize what we just did, we generated a general data set from X, Y, and Z samples. We each time select randomly a number of samples called n random samples. We compute our function, which is also equivalent to the modeling. We compute our integral, and then we append the result to save it. Now we repeat this process over 100,000 times. After finishing the simulation, we can either compute the average final result or just draw a histogram to see the behavior of our system. And that's basically all there is to it. It's very simple actually, yet a very powerful method. It shines mostly when you're using in the multivariable space. I made another Jupyter notebook here that it compares the trapezoidal method with the Monte Carlo method, but just in the 1 dimension, since the trapezoidal is more known for just 1D scale. Alright, so by running this code here, we imported NumPy, Matplotlib, and the time module to measure the difference between the 2 values, or the 2 results. Alright, here I created a function which is a kind of complex function, but in the 1D dimension, having 1 million number of elements. Now we can very easily compute the integral using the trapezoidal function right here. So we measure the time between these 2. And then by using the Monte Carlo procedure, like we just did here, we do the same for this function right here. We choose randomly a y from this function right here. We compute the integral. We append the result. After finishing the simulation, we compute the average and we stop the timer. Now let me run this block of code. Now what you can see here is that whether it's the trapezoidal method or the Monte Carlo method, they similarly almost got the same result, but in terms of time, is the trapezoidal always preferred compared to the Monte Carlo in 1D case? Now we can get a better result by increasing the number of simulation we are doing. Now this will increase tremendously the computational time. It is a bit the reason why Monte Carlo isn't so much used in the 1D case, but more in the general multivariable case like this function right here. And after almost 40 seconds of execution time, the error got even greatly reduced to 0.0034%. Now this was just an overview on how to use it in a more general sense. I hope by watching this video you got the more or less general idea of the Monte Carlo method and the Monte Carlo integration. So if there is something unclear or anything, let me know in the comments. I'll try my best to explain it. Hey, thank you for watching this video till this point. Hope you liked it. I very much enjoy making these types of video, though a like or a subscribe will help me and motivate me tremendously. Feel free to check my other videos. I got some Python tutorials, but also some educational math. And I hope to see you on the next video, and
Peace.